So we would like to invite our first keynote speaker, Professor Chang from Texas A&M. He's an ex-director for the Climate Center in the Texas A&M, and he's an ocean modeler from Mesoscale to global scale. He will give a talk of ocean mesoscale Eddy-Atmosphere interactions along the cultural extensions. Let's welcome Professor Chang.
All right. First, I really like to thank you for the organizer and invite me back to this wonderful workshop. I guess my comments in the last workshop didn't upset you or something. So, and I was also quite surprisingly surprised that when I landed in Tokyo last night, that I found myself to be the first speaker of the day. So. I'm actually struggling trying to put some notes together, so I hope that I won't disappoint you this time for my talk. And anyway, so the topic I choose for this particular workshop would be on the air-sea interactions along the Kuroshio extension region. I saw this is a region which has a very high interest for this group, and so I want to make some point that the small-scale oceanic variability does seem to matter for climate variability and possibly for climate change. So where we go into higher and higher resolution climate models, there's actually new challenges we have to face, and this is something we have to really worry about, I think. So. So this is actually a work by my PhD student who just defended her thesis not very long ago, and so we're in the process of trying to write those results up and for publications. So I hope you find this work interesting. So the motivation for this work, of course, is being this the tenuous connection between the Kuroshio extension region and the Gulf streams and with the atmosphere storm tracks as illustrated by those graphs here. And what plotted here is the net surface heat flux over this very strong western boundary currents region. You can see there's a tremendous amount of air-sea flux exchange. And of course, you notice that the downstream of those oceanic regions, those are the well-known storm track region in the atmosphere. So for a long time, and people have been speculated, there has to be a connection between the oceanic frontal regimes and the storm tracks. But its dynamics is highly complex, and we're not really, in my opinion, we're not completely understanding the connection yet. So, I think as we go to a higher and higher resolution climate models, we'll see that we're going to be resolving those oceanic front regimes more and more explicitly. And then the question arises that how does that can potentially impact the storm track simulation and the storm track prediction and so on. So those are the things I like to talk about today. So let me just show you this animations from a regional climate model, and this is a regional climate model configured for the North Atlantic for the North Pacific domain, entire North Pacific domain, and the model. If I have time, I can show you a little bit detail how the model was constructed. And this is essentially a coupling a WRF regional model to a ROMS, which is a regional ocean model, and both model is actually coupled at 9-kilometer resolution. Right. So what's showing here, the upper panel is showing the outgoing long wave radiation, and you can see, you can of course see a very clear signature of winter storm passing through this sector continuously. Okay, and what is showing in the bottom here on your left is the net surface heat fluxes simulated by the model in the Kuroshio extension region, in this region here. And on the right is the simulated sea surface temperature variability. So what you see very clearly is that, sorry, I have to repeat it again, I hope. So what you see here, there's several features. There's at least two features I'd like to call your attention. One is that you can see there's a very clear connection between the storm activity and the net surface heat flux showing here. So you can see that when the storm passes through, there's definitely change in the surface heat flux. And the scale pretty much is determined by the atmosphere storm scale. So you can see the storm passing through, the surface heat flux essentially lights up, right? So that's one thing. And the other thing you can see is more interesting is that you see this very small scale oceanic feature. And those are the things we call eddies in the ocean, the meandering along the strong western boundary currents. And you can see that their imprints or their footprints are very clearly identifiable in the surface heat flux field. Right? You can see this, for example, I can show you there's actually a cold eddy here which shows up very clearly in surface heat flux field. So the atmosphere definitely feels those very small scale oceanic features, right? So there's really two natural scale here. One has to do with atmospheric scale, which was determined by the storm dynamics itself, and the other one looks like it's more intrinsic to the oceanic spatial and time scale. So if you separate the two by using a spatial filter, which we're trying to do here, so what we did here is that we take the simulated surface SST and surface heat flux, and then we separate the surface SST and the flux using a spatial filter. So we can separate the flux and SST variability into a large scale and versus a small scale. And the separation is about the 10 degree by 10 degree. So we use a filter to, in fact, the half window width of the filter is 15 degree in longitudes, 5 degree in latitudes. So that allows us to separate the two fields. So on the left here, and showing the relationship between the turbulence heat flux and the surface SST simulated by the model. On the right, and showing the small scale SST and turbulence heat flux. So you can see there's actually very interesting difference between the two. On the large scale, right, what you see is that the flux tends to lead the SST by a few days. You can see, for example, here we define the positive flux is actually from the ocean to the atmosphere. So when the storm comes, it sucks heat from the ocean, and a few days later, you actually see a cooling. Okay, so you can see this relationship very nicely. Now, if you do a lag correlation between these two time series, then you get this correlation here. And you can see clearly the maximum correlation occurs when the atmosphere leaves the ocean. So at this spatial and the time scale, it is really the atmosphere is forcing the ocean responding to the atmosphere forcing. You can see as the ocean leads, essentially there's no correlation at all. The two things are not coupled anymore. Now, what is interesting is that on the smaller scale, and you see an entirely different picture. At a smaller scale, you can see the two time series goes almost hand to hand, hand by hand, right? They're tightly coupled, and if you do a lag correlation, what you see here is the maximum correlations occurs at a zero lag, and with a very high correlation, it's almost like a 0.9. So what it's suggesting is that in this particular region, the atmosphere and the ocean are really coupled at a small scale. And the large scale, it is really the ocean, it is really the atmosphere is actually forced to the ocean. And the other very interesting is that normally we associate with the large scale variability with low frequency variability, but this is actually different. You can see the large scale actually tends to have a higher frequency than a smaller scale. And the reason is because the large scale is actually determined by the atmospheric process, which tends to have a much faster time scale, faster and a large time scale. And the small scale is actually determined by the ocean, which has a smaller scale but varies in a longer time. Okay, so the way we think about why there's a coupling between the ocean and atmosphere at this scale is being, you can try to use this cartoon to illustrate that. So if there's a warm eddy forms in the ocean, right, the warm eddy tends to cause instability or tends to make the atmosphere boundary layer more unstable and therefore enhance the turbulence exchange within the boundary layer, right? So as a result, you actually see the deepening in the boundary layer height field, okay, and enhance the vertical mixing or the exchange. So as a result, in this corresponding to this warm eddy, you actually mix a high momentum upper level flow into the boundary layer. So you actually enhance the surface wind speed corresponding to the warm eddy. In the cold eddy, you're actually trying to do the opposite. So I'll show you in a minute, and this feature, that warm eddy corresponds to a strong wind speed, and that relationship has been shown very clearly using high resolution, high satellite observation. I'll show you in a minute. So this is one way one can think about why at the smaller scales, one can actually potentially have a very strong coupling between the ocean and the atmosphere. Okay, so the question we want to ask is that now this small scale coupling has been noted before. There's really nothing new here. So the question we really want to see is that whether this coupling is really local or it has a remote impact. In other words, can those small scale SST feature, the oceanic feature, influence the large scale circulation? Now, if it is only influence the local ocean atmosphere circulation, then it probably doesn't matter very much. There's interesting academically, but in practice, it probably doesn't really matter very much, right? So what we like to see is that potentially this small scale coupling actually can have an impact in the large scale circulation too, and that's what I'm trying to argue and to show you. So the approach we're going to test whether there's an impact on the small scale SST feature or not is by using a WRF-only simulations. So going a 27-kilometer WRF model and configured for the entire North Pacific. Okay, and then we're going to conduct two ensemble simulations using this model. And in one ensemble, we use a high-resolution SST forcing, a satellite observed SST force and a 9-kilometer daily SST for this particular year. And in the second simulation, what we're going to do is that we're going to filter this high-resolution SST, and we're going to use the smooth SST field to force the atmosphere model. Otherwise, the two experiments are actually identical. So we're going to compare the two experiments and to see whether the small-scale SST matters or not. So this approach is very straightforward. So just to give you an idea what we're doing, what we're seeing here. So this is actually the originally observed high-resolution SST from satellite observation. And they're 9-kilometer resolution. You can see, indeed, you see lots of small-scale feature in this satellite observed SST products. And this is what happens if you use a low-pass filter. This is up to filter using this low filter to smooth the SST, and this is the SST feature we get. And this is typically the SST feature you get in a low-resolution climate model. If you don't resolve model, and this is the things you're going to see. Okay, and if you take the difference between these two, you get this. And this is the eddy structure we're talking about. So you can see that the eddies, oceanic eddies, are probably on the order of 2 to 3 degrees. And those things actually have a very long, relatively long time span. So they can last as long as up to a year. The eddies actually, after they form, they survive for a long time. Okay? So if I take the, at each grid point, if I take the small-scale SST and regress that onto the original SST field, and that would give me an estimate to see how much variance this small SST explains, right? So this is this map here. So this map essentially shows you how much those small-scale SST explains in this particular winter the total SST variability. And you can see that in the crucial extension and in the crucial currents region over here, up to almost like 80% of the SST variance can be explained by those mesoscale SST variability. So they're very energetic. They're actually quite persistent. Okay, so next, let's take a look at whether the model can simulate the effects of the small-scale SST. So what I'm showing here is a comparison between the satellite observation and model simulation. Let me explain what those two pictures represent. So the contour here is the high-pass filtered SST averaged over a winter season. Okay, so that's the remnants of the oceanic eddy in this particular season, in this particular winter. Okay, now the color shows the satellite observed the high frequency, the high pass filter, the wind speed. So you can see that the red represents high wind speed and the blue represents low wind speed. So you can see there's a very nice correspondence between the wind speed and oceanic eddies. If there's a warm eddy, you actually see strong wind speed, and if there's a cold eddy, you actually see lower wind speed. Okay, and this is what our model reproduces. So this is using a 27-kilometer WRF model and forced with the small-scale SST. And now what do we do? Instead of using the observed wind speed, we're actually using the simulated wind speed overlay on the SST field. Notice the SST field are identical because we use the same SST to force the model, right? So you can see that it's actually quite amazing that the model seems to be able to capturing very nicely that relationship between the warm eddy and SST and wind speed and the oceanic eddies. Now, it's probably difficult to get the other quantity from observation put in the model, of course, so we can do the other things as well. So, and this is the surface heat flux simulated by this model. And doing the same way, you high-pass filter the simulated heat flux, right? You take the winter mean average. You see that there's a very nice correspondence between the eddy and the surface heat flux. So on top of the warm eddy, we actually see more heat flux going from the ocean to the atmosphere. In other words, the warm eddy gives lots of heat into the atmosphere, and the cold eddy actually sucks heat from the atmosphere to the ocean. And the amplitude of the eddy, the flux variability is a range of 150 watts per meter square. So those are very significant number. Those are not small number. And this is the boundary layer height calculated from the model. As I said from that cartoon, that you expect to see a deeper boundary layer when you have a warm eddy, and a shallower boundary layer in the cold eddy. Again, this is capturing very well by the model. And you can see the boundary layer height perturbation perturbed by the eddy is on the order of 100 to 150 meters or so. So it's about on the order of 10-15%, or maybe 20%, depends on where you are. So again, this is a quite significant effect. Now, this is actually a convective available potential energy, measuring the stability, essentially the stability of the atmosphere itself. Again, you see a nice correspondence. You get higher Cape values when you have a warm eddy, and you're getting lower Cape values when you have a cold eddies. So all this suggests is that this high-resolution regional model seems to be really able to capturing the relationship between the small-scale SST forcing and atmosphere response. Okay, so now the question is that now the model seems to be able to capturing the local feedback or the local effects of the SSTs on the atmosphere. The question is that does this effect actually only confined in this region? Well, that's really interesting. So what we find is quite surprising. So this is actually, we have two simulations, right? We have one simulation, we use the high resolution SST. The other simulation, we remove the small scale feature using the smooth SST to force the model. So if we take the difference of the simulated rainfall response between these two simulations, you get this picture. So you can see that if after we remove the small scale eddies, we get a reduced rainfall along the Kuroshio or the Kuroshio extension region. But what is really interesting is that you actually get enhanced rainfall on the other side of the basin. you actually get enhanced the rainfall along the west coast of the U.S. So what this really, if this is really true, then which means that a small-scale oceanic variability along the Gulf Stream region can potentially have a remote impact on the rainfall on the other side of the basin. Okay, so and not only you actually see the winter mean rainfall is have an impact by the eddies, but the probability of the rainfall also changes when we actually include the small-scale SST features along the west coast, along the western boundary region, along the Kuroshio extension, we actually tends to have a more extreme rainfalls, or we have more intense rainfall activity in this region. And on the other side, you have the opposite. So after you remove the eddy activity along the Kuroshio extension, the intense rainfall tends to occur more frequently along the west coast of the U.S. So it's a very interesting relationship between what happening here and what happening here. Now, this change seems to be quite consistent what we see in the upper atmosphere circulation changes. So what plotted here is the jet streams at the 300 hectopascal. This is the control simulation, simulated by the Wolf model using the high resolution SST. And this is the difference between the smooth SST simulation and high resolution SST simulation of the U velocity at 300 hectopascal. And you can see that along the eastern side of the basin, you see a systematic southward shift of the jet stream after we remove the eddies. Okay, and the picture below here, and this shows 2 to 8 day bandpass filtered eddy heat transport, and this is a measure of so anybody study the storm tracks, and you know that this is a quantity normally used to measure the baroclinic instability, right? The eddy growth. You can see that there's actually a marked change, a decrease of the meridional heat transport along the Kuroshio extension region after remove the eddy. In other words, after remove the oceanic eddies, the atmosphere tends to be more baroclinically, looks like more baroclinically stable and tends to have less eddy growth in this region. And this is the 2 to 8 day bandpass filtered eddy kinetic energy at 300 pascal, the difference between the two models, two model simulation. As you see that consistent with the shift of the jet stream, the southward shift of the jet stream, we actually see an increase of the transient eddy activity along the west coast. And this is exactly the region we actually see enhanced the rainfall variability in this region. So this enhanced rainfall variability seems to be tied together to the enhanced atmospheric storm tracks in this region. All right, now at this point you may questioning that whether this is just a model feature by itself, right? I mean, this is just model artifact, maybe. So the question is that can we see that in observations, which is more difficult, of course. Now, as you know, the Kuroshio current is very interesting, and it's different from the Gulf Stream, and it has a well-defined subdecadal variability. In some years, the Kuroshio tends to be very unstable, and in some year the Kuroshio tends to be very stable, right? And this is actually a construction of the Kuroshio Pass by Kuroshio. And this is a recent paper just published in Journal of Climate. And using the satellite, observed the sea level height variability. So each of these contour represents a particular sea level height trajectory. So you can see that in this decades, for example, you see this the Kuroshio Pass tends to be very chaotic, shifting north and south violently. And this is the year we call it an unstable regime. Right? And then from 2002 to 2003 or 4 in this region, you can see the pass becomes much more coherent to each other, you see less variability, and this is actually the stable year. And then in recent decades, looks like we're entering another stable and unstable regime again. So there's this well-defined stable and unstable regime. No, this is almost corresponds to our model experiment. You can see that this is the region, for example, like we filter the eddies, and those are the regimes that the eddies are very strong. So what we can do is that we can make a composite. We can actually take the trend rainfall, observe the high-resolution trend rainfall, and try to compare the rainfall variability in the stable year versus the unstable year. And so that should give us an estimate to see whether we actually detect any rainfall changes at all from the observation. So this is what we did. So we take this the Kuroshio extension path index defined by Kuroshio in 2014, and then we define those. We take those unstable year, which corresponds to very active eddy variability, and then we contrast that to the stable year, okay, and then we made a composite of the map, and this is what we see in observed rainfall picture. So what we see is that in the stable year, there's actually less rainfall along the Gulf Stream path, consistent with what we see in the model, and we get increased rainfall along the West Coast. Okay, so of course, and this is the probability distribution function of the rainfall, daily rainfall get from the train satellite data. And again, you see a very consistent change in the probability distribution function as we see in the model. So of course, because this data records is quite short, you cannot say this is actually a proof of this mechanism is really working, but at least I think we actually find some consistent evidence with what we see in the model. So what I would like to see is that potentially there is a effect of the ocean eddy on the atmosphere circulation in the storm track region. So the key question next is that how are we going to understand this? And we're still struggling trying to understand this, because normally the scale separation of the atmosphere and the ocean are quite large. Right? Ocean in this region, the spatial scale is on the order maybe 20 to 50 kilometers, while the atmosphere is way over 1,000 kilometers. So there's a huge scale separation. Normally, we don't think the ocean eddy have much of an impact on the atmosphere. Okay, so what we're showing here seems to be the opposite. So how we can think about this? So when we think about this is actually through the Hoskins' classic storm genesis theory. And what he argues is that the baroclinic instability out in the winter storm genesis essentially can be understood as a positive feedback between the upper level potential vorticity and the lower level potential vorticity, right? When the upper level potential vorticity disturbances come through, if there's a very strong SST gradient, you actually can evac the warm currents northward. As a result, these warm currents actually going to induce a lower level vorticity field, which can actually enhance the feedback to the upper level vorticity and cause the storm growth. And that's the classic theory. So this is in the dry atmosphere case, and this is what normally we understand about the baroclinic instability. But in a recent study, and people have repeatedly shown that in addition to this classic baroclinic, what is really important is actually the moisture effects. Because when you have this lower vorticity signal, it tends to enhance vertical motion, which actually can induce additional diabatic heating. And diabatic heating can actually enhance the feedback between the lower level and upper level potential vorticity and cause a much rapid growth of the storm. Okay, so there's some idealized simulation done to illustrate this, and this is just a very recent paper by Lamberts et al., 2012, and arguing that this is the idealized dry atmosphere simulation, and this is the wet atmosphere simulation. And you can see that when you include the moisture, that the development of the vorticity or the cyclones itself becomes much more intense, much more rapid. So potentially that not only that the baroclinic theory, the vertical shear is actually determined by baroclinic instability, but also the moisture can have a very important contribution to the growth of the cyclones. So I think what we find the oceanic eddy effects is through the modulation of the moisture. Okay, and so this is what we find in the model. So if we calculate the water vapor mixing ratio between the two model simulations, after we include a high resolution SST and after we smooth the SSTs, right? And what we see is that when you remove the eddy, the atmosphere essentially becomes drier. In other words, the eddies actually play a role of pumping moisture from the ocean to the atmosphere. So it's not only the eddy is not necessarily changing the strength of the baroclinicity itself, but it can change the moisture budget of the atmosphere. And that, I think, can contribute to the growth of the rapid growth of the storm activity, and contributing to the remote impact of the storm tracks. And so this is actually, if you're averaging over this section, this is the storm mean development region over the winter storm, over the winter season, and you see that there's a quite substantial decrease of the atmosphere moisture content in the lower in the boundary layer and the lower troposphere. So we think this may be the reason why the ocean and atmosphere actually interacts in this region. So why this thing potentially important? I mentioned a little bit earlier that the ocean eddies tends to have much longer lifespans than atmosphere storms, right? The typical storm lasts maybe a few days to a week, but ocean eddies can last for a long time. So this is a time series of the mesoscale eddy variance averaged over the Kuroshio extension region. And again, this nice subdecadal variability shows up very nicely. So if you do an autocorrelation of this time series, which is showing here that this is the autocorrelation, this is the persistence of those eddies, you can easily see that there's a 3 to 6 months lifespans of those eddies on average. So what this suggests is that now if we can include those eddy activity into our climate model, if our climate model is able to simulate those eddy and its interaction with the atmosphere, and then potentially we can actually get more predictability out of those storm system, because the ocean actually carries quite a bit of a memory in the climate system. So I think the potential interest of this study is that if indeed these results what we're showing here indeed really works, then potentially I think as we move into the higher resolution climate models, I think we need to think about how to simulate or include those eddy activity into the climate models, and potentially that can have an impact on the seasonal and the longer time climate prediction in this region. So let me just summarize. And in fact, there's another interesting aspect of this problem which I don't have time to talk about. What we find is that this mesoscale ocean-atmosphere interaction also have an impact on ocean circulation itself, and now that could be a subject of another talk. Maybe next year, if I got invited back again, I can talk about these things. Anyway, so the lessons we learned from this study is that first we see that there's consistent with the observational analysis. We see that the high-resolution regional climate model seem to capturing this very strong ocean-atmosphere interaction, at the mesoscale and the frontal scale level along the Kuroshio extension region. And in contrast, the large-scale SST variability in the region seemed to be really just responding to the atmosphere storm system itself. It doesn't really contains a lot of the air-sea interaction. So that really posed a question whether the AMIB experiment we used to do, where we specified large-scale SST forcing to the atmosphere circulation model, is that really a right approach or not? Shall we actually consider those because from this experiment it argues that a large-scale SST is really responding to the atmosphere variability rather than forcing it. And the second point I want to make is that if you look at the winter season, up to 80% of the SST variance in the winter season along the Kuroshio extension or the Gulf Stream region are really governed by those small-scale eddies. And those things are potentially very important for influencing the climate state. So in particular, what we find is that those eddies not only have a local impact on the atmosphere, and more importantly, can potentially have a remote impact. And what we see that in our experiment, we see that about 20% of the precipitation variance along the west coast can be linked to the eddy activity. So potentially, there's some predictability can be explored here. And the way as I said, we're not completely understanding the underlying dynamics yet. We're continue analyzing this, but our conjecture, our hypothesis is that the eddy influenced the atmosphere through the moisture modulation. It pumps more moisture into the atmosphere. That seems to be the most crucial point. And the last point I didn't have time to show is actually has to do with how this mesoscale ocean atmosphere feedback actually helps to maintain the ocean circulation itself. And what we found was that the Kuroshio extension, for example, itself can be highly influenced by the air-sea interaction. In other words, that really, I think if this is really true, then that also poses a question about how we run our ocean circulation model. Because at the moment, when we run the eddy resolving ocean circulation model, is that we actually impose a large-scale atmospheric forcing. The atmospheric forcing normally is very coarse. Right? The core forcing, we know it's about 2 degrees resolution or more. Right? It doesn't include any of those feedbacks I'm talking about. So that really poses a question if those air-sea feedbacks is really playing a role in constraining the ocean circulation. Are we really doing the right thing when we force the large-scale, high-resolution model with a coarse resolution forcing? So there's something fundamentally. I think there's some fundamental questions we really need to rethink or reconsider when we move to high-resolution climate modeling. So I'll stop here and take questions. Thank you.
Thanks, Pin. Any questions? Professor Yang?
Yeah, this is very fascinating talk. I'm wondering if I can use your second conclusion here to draw another statement regarding current California droughts. Would that mean current California droughts suggest the Kuroshio event is extremely strong activities?
Yeah.
Too strong.
Yeah, well, it's possible. I mean, we haven't really go that far yet. I think potentially, I think there may be an impact. But I think one of the things you have to be, when you draw a conclusion like that, one has to be very careful because in this particular simulation, for example, we didn't include the tropical influence at all. In all the simulation, we isolated the tropics from the extratropics because the regional model allows us to do that, right? You specify the boundary conditions, so all the simulation, the only changes you have in the higher latitude. Now, in reality, of course, you have tropical forcing as well, which can be quite strong in terms of influencing the jet streams, and so trying to separate the high latitude versus the low latitude is not that easy, I think. But potentially, I would argue that high latitude is a potential source as well, especially for the winter season. And this is something we may have to consider. Yeah.
Yeah, hello. It's very interesting. When you look in details on the comparison between the SST and wind speed, the spatial distribution, you can see that they have some space shift. It means that the wind speed peak is mostly at the east side of the core or eddy. It's the east side of the core eddy or warm eddy.
You're talking about this picture here.
You can see that
there's a slight shift, you mean?
Yeah, you can see they have some shift of the wind speed peak and the cold and the warm eddy. Do you know what causing this?
I don't know. I mean, it's interesting.
Yeah,
I mean, there's of course a mean flow here, right?
Yes.
So that could have effects on how the atmosphere is responding to this.
If based on your hypothesis, the wind speed should be exactly above.
I don't think it's going to be exactly on top of each other, right? I mean, the cartoon I'm drawing you. In fact, what we're doing here is a rough analysis. What we should do is actually taking out the individual eddies and following them and calculate the winds directly on top of individual eddies. In fact, we have done that. That's the Lagrangian type analysis. In fact, there's a recent paper in Nature Geoscience by Fraser, and looking at it exactly by this guy here, and look exactly this relationship. And you may want to take a look. And what he finds is that there's indeed a very good correspondence between the wind speed and SST. In fact, a lot of those work has been done by Dudley Charltons and Xie-Ping Xie and others. I think this is actually pretty robust results. Now, the detailed structure, whether there's a small shift, whether that matters or not, I'm not sure about that. But in my explanation, could it be just the effect of the mean flow itself over here?
Thank you.
Just try to, it's very exciting work. Just understand that because the ocean eddy is still very small scale, right, compared to atmospheric circulation. Even for atmospheric eddy in a synaptic scale, it has thousands of kilometer scale.
Right.
So when he moves through the eddies, actually you feel the warm eddy and cold eddy, at the same time, or in a different time. So why? It will produce consistently the less rainfall in the Western Pacific and the more rainfall in Eastern Pacific.
Yeah.
And you were talking about this
the moisture.
Atmospheric eddies.
Yeah.
The heat flux increase, right?
So I'm actually talking about moist baroclinic stability process. In other words, when you have more moisture available in the atmosphere boundary layer, so when the atmosphere storm comes, right, it becomes unstable. You have this interaction between the upper level PV and the low level PV.
Right.
So if you have a moist supply in the lower atmosphere, right, so the growth can be amplified because of the diabatic heating effects. If you have a dry atmosphere, the only thing you have is the shear, is the classic baroclinic stability theory, right? So this moisture modulation can actually modify the storm growth or the eddy growth, atmosphere eddy growth in this region, and that can potentially modify. In fact, we actually, I can show you some analysis we've done. You actually see that the Elysian point flux, so the E vector, is quite different between these two experiments.
Yeah.
So that really shows that the eddy convergence is actually quite different, which potentially change the storm track's position.
Right. Yeah, that's the result. I just understand because the atmosphere eddy is much larger than ocean eddy.
Right.
So when he move over to the ocean,
you
feel the cold eddy and warm eddy.
Yeah, I don't think it's actually the eddy to eddy interaction. I don't think it's that. It's really the rectifying effect of the ocean eddy on the mean state of the atmosphere, which then actually influence the synaptic scale atmospheric variability. And that's why when we take the winter mean average of the moisture, you actually see quite a difference between the two simulations. In one case, it's drier. The other case is it's wetter. And again, this is actually very complex dynamics. We're still working on that. Still trying to understand exactly how to explain these results. But the results themselves seem to be very robust. We did it in many different ways, and the results seem to be very consistent so far. And the other things I want to point out that this eddy structure in the ocean, that the atmosphere follows eddy extremely closely. So it's not like this eddy, it's disappeared very quickly. It constantly falls in the atmosphere because the atmosphere is essentially following the eddies, oceanic eddies. So continuously, those small-scale eddy force the atmosphere. I think that's the reason why you actually see this rectified effects. Yeah.
Yeah, I think that from the ocean to atmosphere part is easy because the ocean eddy actually it's still to the atmosphere is a determinant factor. You fill out the eddy,
Yeah.
or you put an eddy. Actually, you apply a periodic forcing rather than a stochastic forcing.
Yeah.
And more interesting on the inward side. Because I saw other, similar work in the scripts doing this. When you actually, let's assume both sides you can resolve well. So the atmosphere feedback to the ocean eddy is stochastic.
Mm-hmm.
I just don't see how you can, currently we're still to understand. And maybe there's some interesting experiment can be done.
Yeah.
Just by simply just apply. We're still thinking within the deterministic framework,
Right.
two sides.
Right.
But actually, at least one side is a scale mismatch. I think, that would be really interesting. I don't know if you.
Well, I mean, in a way, this is essentially trying to show this scale separation here. This is a large scale, this is a small scale. You can see that the large scale actually happens much faster than the small scale. And this is because the atmosphere varies much faster than the ocean. So at this large scale, we normally associate large scale with low frequency, but in this case, it's actually not. Because the scale is, one is determined by the atmosphere, the other one is determined by the ocean. So there's a natural multi-scale interaction here. So, I mean, the question is that whether how this and this two-scale nonlinearly interact with each other is a question I don't know.
Yeah.
I mean, that's
Nobody knows.
that's really interesting and it's pretty tough
Yeah.
to really understand. But what I'm trying to say is that when we move to a high resolution climate model, and we're about to resolve all those processes, so I think we have to have some way or some idea or some theoretical background to really understand how these two things really start to interact with each other. And we're not quite, when we run the low resolution model, we don't worry about these things because there's nothing there. There's no ocean eddies. Okay. There's nothing to resolve, yeah.
So last question, Chang.
Just a quick question. So your WRF model simulation shows the surface net heat flux difference between the cold and the warm eddy can be as large as a couple of 100 watts per square meter.
Yes.
So do we know how much is coming from radiation, how much from the latent heat?
It's mainly from the latent sensible heat flux. There is some contribution from the short wave and the long wave, basically through the cloud, simulated the cloud in the model, but they're not dominant. The dominant thing is the latent sensible heat flux.
So basically the warm and cold eddy give a lot of very different evaporation scenarios.
Right. That's right. That's the main factor. Yeah.
So we can keep the discussion during the break section. So let's thanks Ping again.
Thank you.